A system response function is convex if symmetric perturbations produce a net positive shift in output. Formally, for perturbations x and negative x of equal magnitude, the average of fx and fx exceeds f0. This means the function curves upward. Gains from positive perturbations exceed losses from negative ones of the same size. Variance in the input is therefore structurally beneficial when the response is convex. Convexity is a property of the response function itself, not of the probability distribution over the input. A system is antifragile when its response function has a positive second derivative, when it is strictly convex. By Jensen's inequality, this means the expected value of the output exceeds the output at the expected input. Antifragility is therefore the mathematical dual of fragility, not merely the absence of fragility. A robust system is neutral. Its response function is linear, and variance neither adds nor removes value. Antifragility requires positive curvature. Robustness requires zero curvature. Fragility requires negative curvature. The three structural categories, fragile, robust, and antifragile, are defined by the sign of the second derivative of the response function. A fragile system has negative curvature. It is harmed by variance and should avoid disorder. A robust system has zero curvature. It is indifferent to variance. An antifragile system has positive curvature. It benefits from variance and can seek disorder structurally. These categories are determined by the design of the response function, not by the magnitude of the perturbations. Antifragility requires that the system remain outside the absorbing failure state to accumulate gains from variance over time. A convex response function that permits entry into the absorbing state is not antifragile. It merely has unbounded upside paired with potential ruin. The distinction is structural. True antifragility requires a hard floor below which the system cannot be driven. Without a survivable floor, the convex region of the response function is irrelevant. Ruin terminates the trajectory before benefits can be realized. Antifragility and survival are coupled design requirements, not independent properties. The Taylor expansion of the expected output around the mean shows that variance enters through the second-order term multiplied by the curvature. When the second derivative of the response function is positive, higher variance increases the expected output. This is the formal mechanism of antifragility. When the second derivative is negative, higher variance reduces the expected output. This is the formal mechanism of fragility. The design implication is direct. The curvature of the response function determines how the system should relate to environmental variance. Engineering for antifragility means engineering for positive curvature in the domains where variance is expected. Antifragility holds only within the convex domain of the response function. Beyond the boundary of that domain, the curvature may reverse, and what was antifragile becomes fragile. This means antifragility is a local property, not a global one. It describes behavior in a neighborhood of the operating point, not across all possible states. Perturbations that push the system outside the convex region may activate a concave portion of the response function. System design must specify both the convex region and the constraints that keep the system within it under worst-case perturbations.